Good morning, everyone. I'm Han Ying from Sun Yat-sen University. Today, I will present our work, AdaSched, a performance-driven cluster schedule for deep learning workloads using deep reinforcement learning. Let me first introduce the background. In cloud data centers, users submit distributed deep learning training jobs to a shared GPU cluster. These jobs are usually long-running, GPU-intensive, and often associated with deadline constraints. In this setting, the scheduler must repeatedly make several important decisions: which job should run, how many GPUs each job should receive, and how these jobs should be placed on the physical GPU cluster. The overall goal is to achieve high user utility under limited GPU resources. Deadline constraints are common in real-world GPU clusters. While these clusters typically possess a mix of SLO and best effort workloads, prior studies like Cronus reveal that over 60% of users submit their jobs with explicit completion time expectations. However, accuracy estimating this completion time is difficult for users. Deep learning convergence is highly unpredictable, depending heavily on factors like model architecture, dataset, and training dynamics. In this work, we specifically target a GPU cluster environment dedicated to jobs with strict deadlines. Another key concept in our work is elastic scheduling. Traditional Gantt scheduling relies on an all-or-nothing approach. A job only starts when all required GPUs are available, and this allocation remains fixed. Elastic training breaks this constraint. By leveraging checkpointing, jobs can dynamically scale out, scale in, or even be temporarily suspended and resumed. While this boosts GPU utilization and flexibility, it introduces a critical challenge. Scheduling is no longer a static, one-time allocation. Instead, it becomes a complex, multi-step, and history-dependent decision problem. Currently, most schedulers use the maximum number of iterations as a completion criterion, but here is the disconnect. Users don't actually care about iterations. They care about the final model performance, like accuracy or F1 score. The iteration count is only their estimation of the training effort needed to reach the desired performance. This estimation can be inaccurate because users usually do not have precise knowledge of the model's convergence behavior. If the estimation is too small, the job may stop before reaching the desired performance. If the estimation is too large, the job may continue consuming GPU resources even after the target performance has already been achieved. The problem becomes more severe in deadline-aware scheduling. Many deadline-aware schedulers use admission controls. They check whether a job can finish the user-specific number of iterations before its deadline. If not, the job may be rejected. But as the figure shows, if a user overestimates the iterations, the scheduler becomes overall conservative. It might reject a job that could have reached its target performance before the deadline. This motivates us to use performance targets rather than iteration counts as the completion criterion. To solve this, AdaSched shifts from rigid iteration counts to flexible performance-based completion. Instead of a single iteration limit, AdaSched allows users to provide multiple performance targets. For instance, an acceptable 90% accuracy and a 99% accuracy. As the figure iteration illustrates, AdaSched dynamic aims for the highest achievable target under current cluster contention. By doing this, we transform scheduling from a rigid binary yes or no admission check into a dynamic optimization problem that maximizes true user value. However, this performance-driven paradigm brings two major challenges. First is the massive decision space. At every step, the scheduler must decide how many resources to allocate and which performance target to pursue for each job. Second is the nonlinear convergence of deep learning. Performance improves rapidly at first, but plateaus later on. This means the marginal benefit of assigning a GPU shifts constantly over time. Because of these challenges, these heuristic policies are often insufficient for such dynamic environments. This naturally leads us to reinforcement learning, which equips AdaSched to make highly adaptive decisions in such a dynamic environment. Putting this motivation together, we propose AdaSched. It first formulates a performance-driven scheduling paradigm. It directly assigns resource allocation with user-specific model performance targets. Then, we design a context-aware reinforcement learning schedule. The policy network uses attention to capture inter-job urgency and use GRU to integrate historical scheduling context. Finally, we conduct trace-driven simulation and shows that AdaSched achieves higher scheduling return and low policy overhead. The main insight is that AdaSched maximizes total scheduling return rather than optimizing only deadline satisfaction or training throughput. To make performance-driven scheduling work, we first need a unified way to quantify the value of different models. To do this, we introduce a scheduling return function. As you can see in this example, the return is scaled from 0 to 100 and is tied to the achieved validation metric. As the model performance improves, the scheduling return also increases. With this return function, we can convert performance-driven scheduling into a return maximization problem. Based on the scheduling return function, we now formulate the scheduling problem. Our objective is to maximize the total scheduling return of all pending jobs. To make this objective meaningful, we consider three constraints. First, each job can obtain the return of at most one performance target. For example, if a job reaches the ideal target, we do not count the return for lower targets again. Second, the total number of allocated GPUs cannot exceed the cluster capacity in each time slot. Third, the selected performance target must be feasible before the deadline. That is, the job must make enough training progress to reach the target in time. This problem can be formulated as a mixed-integer linear programming problem. However, directly solving it is not practical for online scheduling. Therefore, AdaSched uses reinforcement learning to generate high-quality allocation plans efficiently. The figures shows the overall workflow of AdaSched. When job is submitted, it first enters the pending queue. AdaSched extracts the features of all pending jobs and sends them to the IL scheduler. The IL scheduler then decides how many GPUs should be allocated to each job. After that, the placer maps these GPU workers to physical nodes in the cluster. During execution, the performance model tracks its job's training progress, including completed iterations and current model performance. In our implementation, we adopt an open-source ensemble learning approach to predict the future performance trend of each job based on its current training state. The framework is also flexible and can support other learning curve prediction methods. Based on the predicted performance trend and the job metadata, the reward model computes the reward for the current scheduling route. This reward is then used as a feedback to update the IR schedule. Next, I will explain how AdaSched formulates the IR scheduling process. A direct way to formulate this IR problem is to treat the full allocation plan as a single high-dimensional action. However, this does not scale well when there are many pending jobs and each job can receive a different number of GPUs. The number of possible allocation plans grows very quickly. To address this issue, AdaSched decomposes each scheduling run into a sequence of smaller decisions, as shown in this figure. Each episode corresponds to one scheduling run. At each step, the agent selects one job and allocates one additional GPU to it. When the agent selects the null action, the current allocation run terminates and the final allocation plan is generated. In this way, AdaSched changes the action space from choosing a complete allocation plan to rapidly selecting the next job to receive one GPU. This making our training and inference more scalable. The state of AdaSched contains three types of information: static features, dynamic features, and action history. Static features remain constant within one single scheduling run. They include the job type, the remaining schedulable time before the deadline, among others. The dynamic feature is the current resources allocation of the job. This feature is updated after each allocation step within the same scheduling run. AdaSched also includes action history. Specifically, it uses the static features of the job that received resources in previous step. This helps the policy network encode historical scheduling context. Together, these features describe not only the current job queue, but also how the allocation plan is being constructed. Now let's look at our action and reward formulation. At each step, the policy outputs an index. A non-zero index allocates one additional GPU to that job, while an index of 0 acts as a no operation action, ending the current allocation run. For reward design, a straightforward approach will be provide rewards only upon job completion. However, this would lead to sparse rewards, making IO training difficult. To overcome this, AdaSched uses a dense run-level reward. The first term calculates the potential scheduling return of a job in current run. It captures how much useful progress a job can make on the current allocation plan. The second term is a resource allocation penalty. Since GPU resources are strictly limited, allocating more GPUs does not always guarantee better system-level utility. This penalty ensures that the agent uses resources efficiently rather than over-allocating them. Therefore, the reward encourages the schedule to achieve high-value performance targets with minimal resources consumption. Let's move on to policy network architecture. The network takes three types of state features as input, which are first embedded into hidden representations. Because our allocation plan is built sequentially, we use a GRU module to process the historical scheduling information. This ensures the network remembers what resources have already been assigned in the current route, allowing it to make informed step-by-step decisions. Next, we apply attention mechanisms to capture both global and local context. Specifically, One attention module summarizes the overall urgency of the pending jobs, factoring in their deadlines, current performance, and target reachability. A global local fusion module then evaluates each candidate job against this broader context. Finally, the network outputs a policy distribution. After applying an action mask and softmask, the scheduler decides whether to allocate one additional GPU to a specific job or to stop the current run. AdaSched explicitly decouples resource allocation from physical placements. Once the RL schedule determines the GPU allocation for each job, a dedicated placer maps the workers to physical nodes. Specifically, the placer employs a best fit strategy to consolidate jobs onto as few nodes as possible, which maximizes spatial locality and reduce communication overhead in distributed training. Moving on our evaluation setup, we evaluate AdaSched using a custom Python-based simulator, configuring a homogeneous cluster of 64 GPUs distributed across 16 GPU servers. To drive our experiment, we utilize the Microsoft Philly trace and synthetic Poisson arrivals for job workloads, while leveraging a Pulse dataset to map validation metrics to training iterations. Jobs deadlines are defined by a factor lambda multiplied by the job duration in the dataset, with lambda ranging from 0.8 to 1.5. Regarding the RL agent, we trained it using the reinforced algorithm within a two-phase pipeline, offline pre-training followed by online fine-tuning. You can refer to the table for detailed hyperparameter settings. Our evaluation covers a diverse set of deep learning workloads such as image classification, object detection, and speech recognition as summarized in Table 1. For our synthetic trace, each job is generated by randomly sampling a model and its configuration from this table. Because these deep learning tests are inherently long-running and highly resource-intensive, they naturally create heavy GPU contention. This allows us to effectively stress test AdaSched under realistic cluster conditions. We first evaluate the overall scheduling performance using average return as the main metric. As shown in the figure, AdaSched consistently outperforms all baselines across both the Philly trace and synthetic trace. This improvement mainly stems from AdaSched's direct optimization of the user-valued outcome, the final model performance before the deadline. In contrast, Optimus focuses on throughput improvement, Cronus and ElasticFlow focus more on deadline certification. SLAQ considers model convergence, but it does not handle deadline constraints. By uniquely combining performance awareness, deadline constraints, and elastic scheduling, AdaSched dynamically channels resources to the jobs that can achieve the highest performance gains. We next evaluate AdaSched under different resources contention levels. The job arrival rate is varied from low load to high load. Under low load, heuristic policies such as EDF may perform reasonable well because resources are relatively abundant. However, as the load increases, EDF tend to concentrate resources on the most urgent jobs. As a result, other jobs may be starved of resources. AdaSched performs better because it reasons over the global system state. It considers deadlines, progress, performance, and resources cost together. As a result, AdaSched maintains stronger returns even under high resource contention. Looking at the policy execution time, AdaSched clearly outperforms both server-based croners and heuristic elastic flow. Specifically, we achieve up to 5 times reduction in latency compared to elastic flow, and we completely avoid the timeout issues that croners suffers from on large clusters. Ultimately, these results confirm that AdaSched is not only practical for real-time online scheduling, but also highly scalable to larger GPU clusters. To understand why AdaSched makes such effective decisions, let's look at our ablation study. We compare our model against an MLP-based baseline. Because of its simple architecture, the MLP baseline converges quickly at first, but it soon plateaus at a suboptimal policy. In contrast, while AdaSched's learning curve is initially slower, it surpasses the baseline after about 50 epochs and achieves a significantly higher final return. This clearly validates our context-aware architecture. Specifically, the attention mechanism captures job dependencies and urgency differences, while the GRU integrates the heuristical allocation context. Together, they empower the agent to make far better decisions in a complex elastic scheduling environment. To summarize, we designed a novel IO-based scheduling algorithm named AdaSched. It is the first to directly align resource allocation with users' performance target. It transforms DL's cluster scheduling from iteration-based paradigm to a performance-based paradigm. It uses IO to handle the large adaptive scheduling decision space and design a novel policy network to make context-aware decisions. The evaluation shows that AdaSched achieves higher scheduling return with low policy overhead across multiple traces and contention levels. That concludes my presentation. Thank you very much for your attention. I'm happy to take any questions. Thank you.